Welcome everyone. I hope you don't have too strong hangover after yesterday, and I hope you enjoyed the boat ride. My name is Martin. I will tell you first a little bit about myself, just very brief. And afterwards, as Jason already mentioned, we'll talk about simulation and also testing on test beds of automated vehicles. But first of all, thank you again for Jason for the nice introduction, and of course also for inviting us here to this beautiful country and the beautiful island of Jeju. We're pleased to be here, and hope you will enjoy the lecture which I will give you. And whenever you have questions, please always interrupt me. I know that Korean culture is more like being very serious about lectures and letting the professor talk. Please interrupt me whenever you need. Raise your hand or just say, Martin, please stop. Can you explain this once again? Or I have a question. That's not considered rude in Germany at all. We want to do it a little bit more interactive. So even if you're still tired from yesterday, just whenever you have some question, raise your hand or just interrupt me, please. Okay, so first about myself. As you already have heard, my name is Martin. I'm from Germany. They're heading a research group, or actually in the past heading several research groups at the so-called Chair of Traffic Engineering and Control at the Technical University of Munich. We have a big research institute there with around 60 to 70 people. Among of them, we distributed them into 3 different groups. 20 of the researchers are in my group, and my group at the moment has the name Test Fields and Simulations. That's why I'm here, to talk about simulation and test fields and explain you what we do there. And I also have founded a small startup, so this also fits a little bit to this camp, since your focus is also maybe think about will you innovate and think about a new startup idea which you can create either here in Korea or somewhere else. So I've done the same already 7 years ago now, 8 years ago, founding a startup which is mostly dealing with mobility innovation as well. So we do lots of consultancy for OEMs, meaning automotive industry mostly, but also for tier 1 suppliers, so Bosch and Continental, you might have heard about them. They supply a lot of equipment, systems, and products for cars and vehicles in generally, and we also support them with our engineering and simulation skills. Then also, since 11 or 12 years now, or the 12th time actually, I'm teaching in Singapore as well. Also some simulation classes there, mostly dealing with the simulation tool VisSim, which some of you might have heard about already. Who knows VisSim? Some, okay, the majority, great, great. So I'm teaching that there, how to simulate or how to use such microscopic traffic simulation for simulating traffic in Singapore. Also, I'm part of the PARC, which is the World Road Organization. Same like Jason, he's also now a member for Korea. I'm the delegate for Germany in one of the technical committees dealing with road network operation. And I was also for 2 to 3 years responsible for the European Commission in Europe, so that's like our government in Europe, to create for Central Europe an innovation hub. Which is maybe a little bit similar to what I think Kais is doing here in this building. So also lectures, also dealing with startups, helping startups, funding startups, and also encouraging young people like you to found a startup in the mobility field to change the world to a better place, especially in the field of mobility and livable urban spaces. Yes, I've been to US also, same like Jason, to another university on a different coast. And if you want to reach out to me, there's some of my contact details. Also, you find my QR code from my LinkedIn here. I know LinkedIn is not so common here in Korea, especially amongst young people, I heard. But there you find also other contact addresses. So if you ever want to reach out to me afterwards, I will also have my email address here, which you can just write afterwards. All right, so what will I talk again? I will tell you what will I talk to you today, more detailed. First of all, I will do an introduction about the topic. So as you saw, the topic is about simulation, it's about connected automated vehicles, and it's about testing and validation. So I will try to tell you what these 3 elements exactly mean in the field of automated vehicles especially. And I will tell you why do we actually need simulation to do that. Then I will go a little bit deeper into the different details of simulation itself. So which scenarios are we talking about? So for example, urban scenarios, highway scenarios, We will talk about the different models which we are using. We'll talk about the coupling of the different models and different kinds of simulations. So we'll talk about driving simulators, for example, there, but also the coupling with, for example, digital twins of cities. We will talk about verification versus validation. What's the difference and why do we need both of them? I will show you a little bit, since we are in the field of research, an outlook, what is the current state of research and what will happen in the next years as well with simulation. And I will then have a short outlook into something which is very special about my research group, because we deal a lot with simulators. So simulators meaning humans, or people like you, sitting in some technical equipment, like a driving simulator, like a bicycle simulator, and we do some simulations with you as a human being part of a bigger simulation environment. So this is something my research group focuses a lot on in the last years, and that's why I will show you some examples about the tools and systems and frameworks which we are using there. And at the end, we will finish with some conclusions. But first of all, I told you we want to define what is actually the topic about. So Connected Automated Vehicles, CAV, that's the abbreviation. What does it stand for? So connected in this field mostly means it's connected to the environment. So it's connected to other vehicles. It's connected to the infrastructure, so traffic signals, maybe also traffic management center, maybe also some cameras which were installed in the intersection or other sensors to increase the safety by exchanging information with other participants in traffic. So this typically happens via two different kinds of systems. So the one is Wi-Fi. You all know that, consumer Wi-Fi. There's a special Wi-Fi for the automotive sector, which is called in Germany, or in Europe actually, the ITSG5. In US terms, it's very often referred to as DSRC, Dedicated Short Range Communication. So this is just a Wi-Fi which was optimized for the use in cars, which means that it can also operate while driving high speed or higher speed, and it has longer ranges than the typical Wi-Fi you have in rooms or on your smartphone. So we use this technology to communicate or to enable the communication between different cars so that they can, for example, exchange information about hazards on the road, about maybe an emergency braking, which they will activate in the next seconds or milliseconds. They can also exchange information about the traffic state, about maybe pedestrians or cyclists they have detected with their sensors, and other cars which are maybe driving behind did not see yet, so exchanging safety relevant information. Mostly, but it can also, of course, be used for infotainment or for other information, for example. So this is typically what is done nowadays. Additionally to that, we have the possibility to exchange information via cellular network, so the typical mobile internet, 5G and 6G, so sixth generation, which is currently on the verge of also being implemented. So this is two communication technologies for the vehicles to exchange information. And automation, and of course, I mean, this is a term which is used widely nowadays, especially in the field of traffic. Vehicle automation is mostly defined as the technology which is used to have a driverless car, to simple spoken. So replacing the driver's activities and the operational, tactical, and strategical operation of a vehicle by algorithms which are fed with data from sensors and using a lot of computation power in the vehicle. So that's the definition of automation, what we call here. There's very often also the used autonomous vehicle being used. We in research in Germany, or at least at TUM, we try to avoid this term because autonomous, according to our definition, would mean no external information, no external influences. So fully autonomous without any interface to the outer world. And this is somehow a little bit neglecting then the connected part here. Okay, so connected in our field means, again, receiving information from from the environment, from the infrastructure, also from other vehicles. So according to our definition, this would not make an autonomous vehicle autonomous. Therefore, whenever we talk about driverless vehicles, we use the term of automated vehicles, or fully automated, or highly automated, just for the definition of the terms here. So that's connected automated vehicles. We will talk about that today, and we will talk about some examples also. So I will show you later something which I've brought here on the left-hand side. I think some of you might have joined Jason to Munich. Some here in the room might have seen our automated rickshaw, which is a 3-wheeled vehicle, very light vehicle. I'm actually not sure how much it weighs at the moment. It depends always which computation power and sensors we install, but it's something like between 120 to 190 kilos. So very lightweight vehicle. We can actually carry it with 3 people easily, or not easily, but we can carry it. We also have nowadays on Munich streets, and especially in the north of Germany, also Moja operating. This is a brand from Volkswagen, from VW, which is operating such autonomous shuttle buses. We have automated trucks, we have automated people movers. So all these are examples for automated vehicles. Who has ever driven an automated vehicle? Or who was ever passenger in an automated vehicle here? Not many. I'm not so sure. I actually wanted to check it yesterday. The Seoul metro is not automated?
Metro?
The metro in Seoul?
Some of the metro lines.
Yeah, I think all of you have driven automated vehicles already. I didn't put the metro here, but this is also an example for an automated vehicle. Yeah. And the others, they have driven automated people mover like that, I guess, right? Like small shuttle buses. Yeah, that's a typical showcase nowadays. So whenever we talk about automated vehicles, typically we think about automated cars. But of course, there's also automated trains, automated tram lines on the road, automated 3-wheeled vehicles, maybe automated small logistics robots or parcel delivery robots. Yeah, maybe also automated drones. I will not talk about that. But there's lots of kinds of automated vehicles, and I think especially when you think about public transport, metros, maybe also buses in the future, bigger buses, we will see quite a step in automation there in the next years. Therefore, since you see that they will be part of our future sooner or later, it's very important that we test and validate them. So what does that actually mean? And I brought you now a lot of examples why we need to test automated and connected and automated vehicles. So first of all, of course, safety. That's the main reason why we already do testing of regular manual-driven vehicles, so to test if they're safe for operation and safe for the humans which are using them, but also safe for the humans in the surrounding of these vehicles, pedestrians, for example. So that's a very important part also for the testing and validation of automated vehicles. Then, regulatory compliance. Lots of authorities worldwide have already established the first rules, the first laws, the first descriptions, technical specifications about how automated vehicles should be equipped and how they should operate. So to fulfill these regulatory framework, it's a very important part in our testing procedures that we test according to these frameworks. And of course, error detection. So in the development of such vehicles, we will definitely do lots of errors. It's hundreds of millions of lines of code probably, which are at the end in such a vehicle. So you can imagine there's lots of potential error sources. So therefore, to detect and correct these errors during the development process of such vehicles or of such algorithms for such vehicles is a very important task. Cybersecurity. So you probably have seen also some documentaries or read some news articles about automated vehicles which got hacked or regular vehicles which got hacked. So cybersecurity is really an issue because you can imagine if the vehicle has the possibility to drive, to accelerate, to stop on its own, and this is all happening via algorithms, and these algorithms might be vulnerable to cyber attacks. This is a big risk for the passengers in such a vehicle. So therefore, this also plays an important role. Interoperability. So we need to test and validate, do the vehicles actually, are they able to work together? So is a Toyota and a Mercedes car, can they actually work together on the road? Can they also, as I mentioned before, be connected? So exchanging information about other vehicles in the surrounding, about hazards on the road. So they need to be able to communicate to each other. They need also to be able to communicate to the infrastructure in the city of Munich, but also on the island of Jeju. So they need to follow certain standards to work together as a whole. So this is also a very important factor. We have the field of data accuracy. So ensuring that actually the data which is gathered in the vehicle and which is also used in the vehicle is accurate and is the same like what we can observe in the real world. Then we need testing and validation because we want to refine and advance technology by identifying areas which can still be improved. So we need to find the gaps in our software and our hardware which we can still improve also during the development process. We want to check the reliability and performance of such vehicles. So are they really better, for example, than human drivers? Are they safer? Are they working more efficient in our traffic system? Do they really bring positive impact to our mobility system? That's also something which typically is not done by the car makers. They don't care so much about, is it really efficient in the overall system? Is the city system, the city mobility system getting better? That's task of us researchers, for example, by microscopic traffic simulation, to validate if they really bring a positive impact on sustainability, so less fuel consumption, for example, but also efficiency of the transport network, less congestion, less travel times, and the same for safety, less accidents, less dangerous situations, or at least reducing the severity of an accident via smart systems. Yes, I think this is all quite clear. Also edge cases we have to test. And more important at the end is consumer confidence. So I'm not so sure how it is here in Korea, but in Germany nowadays, when you talk about automated vehicles, the first thing you hear from the people which are not working in the field is, I don't trust that, it's not safe. Because we did have some examples. I mean, you heard about crashes of automated vehicles, I guess, in the US, where they're already operating on the streets in bigger scales. People are getting injured. Some do even have some fatalities involving automated vehicles. I mean, there are very few, probably especially very few in comparison to what we have with human involvement. But still, this has a big impact on the consumer confidence that this is a safe and good idea in the future to transform our mobility system towards this direction. So therefore, to see if the consumer, so if the passenger actually at the end, feels confident in using such a vehicle, this is also a very important part of testing and validation. Not just if he feels comfortable inside in terms of the environment in the vehicle and the nice seat and whatever, but if he feels safe. That's also very important, and we do this by showing the consumers or showing the passengers in testing, in test fields and test beds, first of all, how it is to drive in such a vehicle or to be driven in such a vehicle, but also how it is to interact with such a vehicle. So on the roads, if you're a pedestrian, can you really feel safe if you, for example, walk on a sidewalk or walk on a pedestrian crossing and the vehicle is suddenly approaching? So we show this to the people by bringing these vehicles on the road and testing them also in public roads. This I will talk to you about in the second lecture. So that was lots of theory. Let me explain you how we typically do that in practice. So typically what we do, we have 5 different areas where we look into how vehicles operate and what their effects are. And I think I see lots of you making photos of the slides. I think we will share them afterwards, right? Yeah, so you will get the slides afterwards. The only thing, I'm not so sure about the videos. Yeah, it's even recorded, so you don't have to make photos. You can, of course, do make photos. That's not a problem, but you will share the slides afterwards. So that's the 5 fields where we actually do testing, or the tools which we use for testing automated and connected vehicles. First of all, very basic way, data analytics. So we just get data from other automated vehicles, from car makers. We record them by ourselves. We use drones, for example, to fly over automated vehicles to record what is happening with them. Because typically the car makers, they don't share their very secret algorithms with us, so we cannot evaluate them. So typically what we do, we observe them from an external point of view, cameras, drones, etc. We do simulations. So if we have algorithms about how these vehicles do operate, how the automated vehicle driving algorithms works, then we can use them, feed them into simulations. So you already see here the VisSim simulation from the PTV group. We use also Sumo and Imson, for example, for that. And I'll show you later, we have lots of simulators, which we will also use for evaluating how do humans, for example, interact with an automated vehicle, or how do humans feel when they drive, when they are driven inside of an automated vehicle. And then we go one step further, so leaving the computer world, leaving the simulation world, going to real test beds. So for real test beds, I think would say even the naming is not so sharply divided between these two. We have two different kinds. We have the experimental test beds, which is typically private test beds where there's a fence around it and no civilians can enter, so no pedestrians, no cyclists, and where we can do whatever we want because we don't have to follow any regulations for public roads. That's what we call typically the experimental test fields or private test beds. And then we have real test fields, which means we really bring the vehicles outside on the road in a real city. We just drive around in Seoul or here around in Jeju Island with our vehicles. This requires the most work, I would say, because first of all, then you have to fulfill all the regulatory requirements. You have to make the vehicles very safe. You have to convince the authorities that you're allowed to operate. It's a huge financial investment. Of course, lots of things can go wrong there as well. You don't control the whole situation around the vehicle anymore, like what you do typically on experimental test fields. And of course, if something happens, there is always somebody with a smartphone camera and recording it. So if you do something stupid or if you do something unsafe, you can surely find it on the next day, either on YouTube, Instagram, or in the media. So therefore, this is something which you should only do if you're in an advanced state. So this is also why I ordered it like that. So typically, the very basic analytics goes from left to the very complex testing and validation on the right. And we will talk in the first lecture mostly now about simulations and simulators. And then in the second lecture, which will follow afterwards, oops, sorry for that. We will talk about the right part of this chain, of this process chain, where we will talk about how we actually bring those vehicles to the street. But first of all, simulation. Why do we actually use simulation? So this is now valid not only for testing of automated vehicles, but in generally, simulation, why is it, does it make sense? So first of all, I've already told you, the more left we are on this process chain, which I've shown you before, it's easier, it's simpler, and it's cheaper. So simulation, I mean, you have already an equipment in front of you, your notebook, your laptop, where you can just do simulation. You download the software. Some of them are even open source and free. So it's very simple to do that. And typically, we also do that to save time. So to accelerate testing cycles, that's a big plus for our simulations. And we use it to test huge amount of scenarios, which I will show you later. We can have reproducible results, meaning that we can simulate something, and if we found some errors and want to try it again afterwards, we just simulate it again under the same environments, because in a simulation we control the environments. So we can have reproducible results because we control all the boundary conditions. This is a big plus for simulation. And we have valid conditions which we can verify with the reality, for example, by collecting data. And of course, especially when we talk about automated vehicles, we do have a safe testing environment. So if we do have an accident, or even like we run over a pedestrian in simulation, well, that's bad for us because we have to invest more time, but it's not a problem at the end. If we would ever injure some person on the street with an automated vehicle, that would be really bad. So safe testing is, I would say, aside from the cost effectiveness, probably the main reason why we use simulation nowadays. And there's different kinds of simulations. So probably you've heard some of these names. So for example, model in the loop. This means we have the model already developed and we test it in the simulation. So we run the model. Then what the next step would be, for example, we have not just the model of, for example, an automated driving algorithm, but the real software. We got it from BMW, how they operate their vehicles, and we use this software in the loop. So we can test the software, the real software, on our computer. One more step is hardware in the loop. So for example, we are using sensors, LiDAR sensors, real LiDAR sensors, which are connected then to our simulation. And the LiDAR sensors, we fake the environment for the LiDAR sensors so that we see how the LiDAR sensor, the hardware, would actually work. You can also, hardware in the loop is similar, for example, maybe for a driving simulator on a testing ground from the vehicle certification. So there also you have a vehicle which is driving on a testing test interface, but we really have the hardware operating like on a regular street, just in a testing facility. So this would be hardware in the loop. And vehicle in the loop overall is then that the vehicle sensor, for example, also the cameras get, for example, a fake image on front of them on a screen. That we bring a digital twin, for example, of the surrounding in front of the vehicle, so that the vehicle sensors think they are driving on a real test bed, actually, but they are driving on such a vehicle stand. And last but not least, something which was in the past very often called driver in the loop. And nowadays, since we talk also about automated vehicles, of course, it's not the driver anymore. So we are now trying to call this rather human in the loop. So somebody like you, a test person, coming to our lab and driving our simulators, this would be human in the loop testing. So it's still a simulation. So you are in a simulated world. You see on screens, for example, like here on a driving simulator, the virtual surrounding. And this is what we call human in the loop simulation. So again, also you see here from top to down, you see the more complexity when you go down, and of course also the costs and the time consumption of these simulation types increases when you go down. Yes, but of course costs go down, costs go up, and reality goes up. That's the big plus which you see here. So which tools do we use? I think I can skip this fast because we already talked about it. We have typically microscopic traffic simulation for the traffic which we simulate. Sumo is nowadays used quite widely. It's an open source tool. Vissim I already mentioned. And we use also lots of what we call microscopic simulation tools. So going into more detail, looking in the vehicle surrounding, looking at the sensors, looking at the algorithms. Typically Unity 3D, it's a game engine actually, is used quite a lot. Carla, Prescan, ROS. So lots of tools there, and there's much more tools on the market available. The domains here in this field, they're really merging together. So you will see we use game engines, we use software from computer science. We use lots of AI in our software nowadays, machine learning algorithms. So the domains are really merging together. So it's quite difficult to really show you here a chart which all the software which is used in this field because it's changing rapidly every day. So you have probably already seen how microscopic simulation looks like. So this is now an example. This is an old video of Vissim, so where we simulate the traffic in cities. So this is typically not too detailed. So typically we look there at several thousand vehicles which were operating in our city network, and we simulate rather what is the impact of our algorithms, of our systems, of our products, of our innovative mobility solutions on the whole mobility network in a city. So it's rather to evaluate efficiency of traffic and also safety of a mobility system. If you go one step more detailed, that's what we call a driving simulator. So driving simulator means some human in the loop, somebody like you. I think this is even a video of me driving in a driving simulator, doing some illegal overtaking in the city. So this is fully movable cabin where you drive a real vehicle, so the software is also from a real vehicle in a simulated environment. And there is also something which we call dynamics driving simulation, or driving dynamics simulation. So this is something which is really focusing on one vehicle, very detailed. So we have, for example, the bumpers of the vehicle, the brakes, the acceleration behavior, also the tires, the tire structure. So really lots of details about the vehicle in our simulation model. And can, for example, simulate here an overtaking maneuver which turns really critical because of the wet surface and the slippery surface. So this is the different kinds of worlds, I would say, which we have in the field of traffic and vehicle simulation. And you already see now that they are nowadays very much overlapping. So it's not quite easy anymore to differentiate between them, because very often such simulations can include also much more other vehicles. We can also have in such a simulation a driving simulator being integrated, so you actually drive this vehicle in this simulation tool. So they become closer to each other, and the systems really are interoperable now. So, here we go. And I already mentioned before, typically we test in lots of different scenarios. So for example, urban environments, highway scenarios, so freeways where we do have higher speeds and maybe probably hopefully no pedestrians, no cyclists. We test adverse weather conditions like you showed you in the video before. And we also simulate complex traffic situations. So for example, situations like construction sites, which are not so easy to identify sometimes for vehicles, or traffic situations like here, where it looks quite unorganized and where vehicles which are automated might have quite some problems to operate there in a safe and efficient way. And we also have lots of research nowadays with the interaction between vehicles and the surrounding vulnerable road users we are used, which is cyclists and pedestrians mostly. So, what other areas do we have? I think I will just skip that a little bit because I think you have a lecture on simulation as well, right? I guess, so let me just skip that due to time reasons. Oops, okay. What is more important and what is really a main task in research at the moment is the 3D city models. So as you have seen before, all these simulations require that we know something about the environment where these simulations happen. So the environment is typically our cities, or at least our transportation network. So therefore, what is our main task really is to bring these real world situations into our simulation models. This is really, first of all, the first step you have to do, and second of all, typically also the most time-consuming step. So bringing the real world into some digital world, which is the surrounding afterwards for our simulation. We typically call this a three-dimensional city model because nowadays the requirements of simulations is very often that we need the third dimension as well. So for microscopic traffic simulation, 2 dimensions, totally fine. For all the other simulations which I have shown you, the third dimension is a must. Because, for example, you need to see when you're driving in a driving simulator, you need to know where is obstacles where I cannot look through. Where is obstacles which are obstructing the view to other vehicles, to pedestrians or so on. So the third dimension is a must there. And if you look into the field of automated driving, obstruction becomes even more important because the automated vehicle requires to rely only on sensor data. LiDAR sensor, radar sensor, cameras, whatever. And those need not only the information about is there obstruction in front of them, but they need information which material is that. Is it wood? Is it glass? Is it reflecting or not? Can I look through or not? So this is a very important information for 3D city models to be implemented in simulation. And that requires a lot of work, you can imagine. I mean, I don't know how many buildings the city of Seoul has, but I guess it's hundreds of thousands, if not even millions, probably it's millions. And having the information about the building material of all of them, and it's not only one building material, but there is also windows, and then there's some special other infrastructure in front of the street. There's trees which are changing their shape every season. So there's lots of information which you have to include to be able to have a realistic simulation environment. Accurate data. So we have to maintain the accuracy of the data because sometimes it might change. We might have a construction site for 2 days. Automated vehicles need to know that. So therefore also we need to enable an update cycle, which is helping us to keep it up to date. Yes, infrastructure planning. So I'll just skip that here. And at the end, of course, what we still have to do, cost saving. So simulation, I told you at the beginning, is a very cost-saving alternative for testing in the real world. But you will see recreating such a digital twin is quite costly still. So therefore, this is really an important thing. And we very often use also the digital twins afterwards for public engagement, meaning that we will use those for visualization of our results, for representing in our digital twin, in our 3D city model, representing this to the authorities, to the politicians, to the decision makers, but also to the public audience to encourage them to, or not encouraged, but to convince them that we are doing a good job, or that this change which we do is a good idea for the future of the mobility system. So public engagement is quite important nowadays, to communicate not just the research results towards the public, but also to involve them at an early stage and consider their needs, consider their requirements, consider maybe what they're scared of. So this is a very important part nowadays of our research. That's why very often we do the simulator studies, not with researchers or students, but we just invite regular people. Even my 65-year-old uncle was participating, for example, last time in a driving simulator study, just to involve the people and see what they are actually afraid of. So because you can imagine they are having a different opinion on automated vehicles like we as researchers have. They have a different opinion on traffic which is different than what you have as traffic engineers. Okay, let me just see the time. We make a break at 10:45, right? Okay, now let me just continue with that a little bit. Yeah, maybe just that you don't be scared. My first part is a little bit longer, second part is shorter, but we make a break in the middle, okay? So the first part will also continue in the second 45 minutes. So, simulations and models. So I told you at the beginning, the domains grow together much more in the current time and in the future probably even more. That's why typically what we do, we couple the different domains. We couple the different models from different domains. We couple different simulators with simulations, with real-world testing. So this all grows together. And typically what we have done in the past, also I think when Jason was at our institute in the past, we were dealing with the traffic only. So we did microscopic traffic simulation. We were not dealing with vehicle technology. We were not dealing with pedestrians so much. A little bit with cyclists, but also that was a very small field. So we just dealt with car traffic on freeways and car traffic on urban roads. That's what we did. Nowadays, we have to look much more detailed in the field of vehicles. You can imagine with all the vehicle advancement, not just in automated driving, but also the driver assistance systems which we have, with all the new kinds of vehicles, like rickshaws on our street, like these people movers on our street, like small delivery robots on our street, it becomes much more important to understand what is actually happening on the vehicle side. How do they behave? Which algorithms are responsible for moving them to the left, to the right, accelerating, decelerating, and so on. So this is really becoming a field which is becoming very important in our field in traffic engineering to understand what the vehicle is doing and to use dynamic simulation to establish driving simulators. And, as mentioned before already, three-dimensional city models. This is something which we have not dealt with in the past. When we imported something in our microscopic traffic simulation, it was a two-dimensional plan, sometimes even just a screenshot from Google Earth, which we just then tried to replicate. Nowadays, the 3D city models become very important. So we also need to have the knowledge how to create them, or at least how to assist somebody in creating them. We have to have the knowledge how to use them, and we have to have the knowledge how to couple them all together. So coupling of these two different domains really becomes our main task nowadays. And I think this is my last slide and then we do the break. So the benefits of coupling are very important nowadays for us because it makes our simulations more realistic if you use vehicle behavior which is coming from much more detailed information. We make our dynamics simulation more realistic because we because we include the surrounding traffic into our vehicle dynamics simulation. In the past, vehicle dynamics simulation from automotives were only always dealing with one vehicle. There was maybe another vehicle driving in front of them, which was scripted, so it was defined how it turns, how it accelerates, and so on, but it was not a realistic behavior. So what we do now, we bring our 1,000 surrounding vehicles and pedestrians and cyclists from our microscopic simulation domain into the vehicle dynamics. So suddenly, they have a realistic environment where their one vehicle is operating. So this is also very important. And also our driving simulations become more realistic because we use the 3D city models and we integrate them into all our simulation environments. So it's not just it's not only that it looks nicer, but also our vehicles can drive in a real and more realistic environment, and also our humans can drive in a more realistic driving simulator environment. So all these three domains which we now have put together really benefit from each other. And what I will talk about later, after the break, is that we require very complex interfaces between these three different domains. And this is something which I will talk about after the break. So thank you very much for your attention, and see you later.
Before the break, can we have as well just a short questions?
Yeah,
Some of the questions
of course.
or comment? Yep.
Can I? Thank you so much for the wonderful talk, and I really love how you kind of engaged. I'm a social scientist, disclaimer, engaged social scientific elements into your talk. But in my field, I do AV policy, and in my field, the thing about simulations, and I can see that lots of things that you've done is to basically try to make the whole simulation more realistic, including 3D modeling and so on. But there's no ramification to your action. There's no real ramification to your action, right? So if you actually hit someone on the simulator, you don't actually hit a real person in real life. So people's behavior might actually be different. How do you reconcile that?
Yes, that's why I have a second part of my talk about the testing and test beds. This is exactly the big criticism about simulations. I will have a nice quote later on which says, all models are wrong. That's true. Simulation is always wrong. We try to get closer to reality by improving them from year to year, but they're always wrong. That's why for such situations, of course, you need to have real world testing. That's a must, and I'm totally with you. In our simulations, for example, when we have an accident, nothing happens. So you cannot punish the driving simulator person and saying, oh, you did wrong, you go to jail now because you were driving over a simulated person. So it's completely different. And for example, also the behavior is different because they don't get charged fines for overspeeding and so on. It's not that just accidents, but the whole behavior is different. There is possibilities to make such study designs in a way that the test persons are behaving more, more realistic. So for example, you tell them you are testing for something completely different, so they pay attention to that, and actually you're testing something completely else. That's what we very often do. But at the end, I'm totally with you, this is just the first step for evaluating it in reality afterwards with real test situations. Of course, we can also not test accidents there, but again, we can have, for example, like puppets in front of them. And then, the feeling of being scared, of running over something, is quite similar to running over a person, I think. I did it once, I was participating at such a study, and I was not driving, I was just a passenger. And they didn't tell us that we will run over a pedestrian. They were not throwing it, but it was on rails, and the pedestrian was being driven on rails. The puppet was driven on rails in front of our vehicle, and suddenly we crashed it. And it was feeling like we had a real accident, for me at least.
What are the ethical issues of that?
Yes, we have. Yes, that's also
sorry.
a good question. we are in very deep exchange with the ethical commission of the TUM. I never had contact with them before, but when we started our simulator studies and then the real test beds, we had lots of talks with the ethical commission. As long as humans are involved, you have to have long discussions with them. And this is something which I have never done, so we don't do this on our test bed. We don't do such safety critical situations because in the end it might happen that the driver of the vehicle just is so scared and he hits gas pedal and hits, I don't know, the wall or something like that. So you don't know. So this is what we don't do, but in such situations you have to consider ethics a lot.
And you have to go somewhere. If you want to do some very critical situation, then you have to go somewhere.
Yeah, what I will also show you later. When we do our testing on our real test beds, we don't do safety evaluations anymore. There is experts doing that. We are not the experts for that. So typically what we evaluate is, do the systems operate in an efficient way? Are they reliable in terms of, for example, that the communication works, that the algorithms steer correctly, and how do the passengers actually feel in such a vehicle? Not when they crash into a pedestrian, but when they drive around the curve. So very simple situations. That's what we test. There is, TÜV, for example, and I'm not so sure what is the certification authorities. They do such real tests with such vehicles where they really crash into something, sometimes even involving test persons, which are at least observing the situation. So this is something we don't do. So safety critical testing in real world, we don't do this with autonomous vehicles. I hope we will also not do this in the future.
Just be curious. So what kind of simulations are you guys using for your research? Maybe VisSim, and then
A lot of wisdom, right? You know Sumo as well? Yeah.
and what else?
Carla, okay, yes. Yeah, that's quite a common one. Any other simulation tools which you're using, which were not on the list maybe even? Unity, yeah. Okay, yeah, sure. MatSim, yes. Yeah, MatSim is a very powerful solution. So we also have MatSim combined with ROS sometimes.
Well, sometimes, I felt kind of stressful because there are so many simulations, and each simulation has a good thing and bad thing. And for the purpose, according to the purpose, I have to learn this simulation A, and for the next project, I have to learn about the other simulation. So sometimes I'm thinking about we need some kind of a godfather of the simulation. So one simulation can handle any kind of purposes. Do you think? Is there any kind of candidate simulation model?
I don't think so. I mean, maybe some big IT company like Google is working on that. But what we are using at the moment is really individual tools and coupling them. That's what our main use for such simulation is.
What about Sumo? Sumo for macro and micro as well?
Yeah.
Or just micro?
So that's why I highlighted it before. I was writing Sumo on Bold. That's the main tool which we're using at the moment in this microscopic simulation world. But to be honest, it's not because it's the best one, but it's because it's easy usable, because it's free, because we have lots of projects which are requiring Sumo. We have lots of people who already know Sumo. So if you would have hired more people who know VisSim, then maybe VisSim would be our tool. So it's also about the pre-education of the people. Also our customers, what they require. So sometimes a city comes to us and say, please simulate traffic in our city. And then it depends on which model they already have for their city. So they will give it to us. So if it's then Aimson or VisSim, then we'll just use that. We will not create a new model. So I think it would be important to choose always the right tool who has the right application area for a certain project. But at the end, it's almost never like that because you have so many boundary conditions, knowledge of the tool, existing infrastructure or existing model already. So you never choose the right tool, I think, at the end. Yeah.
Okay. Question, comments?
Yes, please. You were a little bit faster. Yeah, you. And then you afterwards. 2 milliseconds later.
How much do you think the visual quality of this simulation program affects the driver behavior? If you're using simulation program such as Unity, it's pretty hard to make the environment look the same as the real environment. So does it have an effect in how in the driving behavior?
So yes, absolutely. I think the effect of the realistic environment is even smaller than the effect of the realistic perception of the environment. So for example, perception of distances, perception of speed, this plays an even more important role. So when we create, for example, now we have a 190 degrees, I think, screen around our driving simulator, and we don't focus so much on the quality of the of the buildings, of the material, that the trees looking super realistic with each leaf being there represented. Even so, this is important, but we rather look how is the perception of the driver. So is the tree, when we move with the car, does it feel like it's now 3 meters, or does it feel more far away? Does it feel like we're really fast when we pass by? So it's more like about perception than about the realism, or more about the perception than the quality, I would say. So when you say we want to make it more realistic, we look at these factors and not at the resolution of the screen or the resolution of the graphics. That's even more important. But yes, I mean, at the end, we also have tests, for example, now with virtual reality glasses, where you have more immersive feelings or more immersive perception. There, again, I think it feels much more realistic, and also when you turn around, the movement is much more realistic. So you feel like you're in the real world, but at the end, this has the negative implications that the people feel very dizzy. So they can only do short tests, or I would say 30 to 40% of our candidates, they feel so dizzy that they have to stop the simulation experiment. So therefore, we again went back to the screen, because then we know that everybody can drive until the very end and we have more data. Even so, maybe the data is not that realistic. So it's never perfect, and it's still a simulation. That's why afterwards in the second lecture, I will show you about the testing in reality is much more better, because you get more realistic data just. So now to you.
Thank you for the presentation. And my question is, you mentioned the building safety is very important. Then how can you get the pedestrian and drivers building safety?
So typically when we talk about sitting inside the vehicle, typically to make them feel safe is of course the movement of the vehicle. So no harsh braking, no harsh acceleration, but also giving them on a screen, for example, the information, what does the vehicle see? So for example, when you nowadays drive in vehicles, sometimes they have the overview also, I see this and this and this vehicle, I see here the lane marking, I see this tree. And when you see what the vehicle sees, then you trust the vehicle movement more. Of course, if you see on the screen, the vehicle doesn't see this truck, that's bad. Because then you think, that might be a dangerous situation. But you trust the vehicle much more when you see what the vehicle sees and see the interpretation of the vehicle of the surrounding. And as on a pedestrian side, for example, what we do very often, it's nowadays in simulation studies, we communicate outside of the vehicle, for example, on a screen, I have seen you. So there's, for example, a sign when you want to cross a pedestrian walkway, that the vehicle has a screen there saying, I have seen you, you can safely cross, and it also slows down. So this also increases the perceived safety of the pedestrians then.
But I think sometimes we cannot figure out which part make me feel unsafe. So I can only feel unsafe, but I don't know actually which part is making me unsafe. So yeah, but that part I think the simulation, you also mentioned the simulation has some drawbacks.
Yes. I mean, this is what we call subjective safety. So you don't know exactly why you feel unsafe, but you don't feel so safe. Typically, we do this afterwards with questionnaires. So we ask the people, did you feel safe on a scale from 1 to 10? Sometimes even with a touch screen in the car where the passenger can say, now I feel unsafe. And of course, they sometimes cannot say why, but we can maybe use lots of data to evaluate, okay, this is the certain boundary conditions which seems to make the people unsafe. That's, I think, the only thing you can do in such this. Yeah. But maybe you can ask afterwards our social science expert. I guess she has a lot of things to say about that.
And I have another question. Maybe it's because maybe there's a computer game in City Skylines.
Yes, I know that even.
So that kind of game, every people in there is controlled by intelligent agent. So they can also have their interaction in the in the environment with you. So what do you think? Do you think we can also do some simulation in that kind?
Yeah, I would say so. Well, I'm not so sure how advanced, for example, the traffic models is there. And I only know a very old version of that game where I just know the big criticism was that for the traffic system, parking was not considered, which is a big thing, a big space consumption in cities. So if you completely leave out parking, I think our cities become much more denser, much more nicer, and so on. So I'm not so sure how advanced the traffic model is there. But I can assure you that from the gaming industry, they do really big advancements in also vehicle behavior. So if you look at nowadays at high-end computer games, their behavior of the vehicles on roads is very realistic, sometimes even more realistic than 5-year-old traffic engineering professional software, because they invest a lot of, or they use a lot of data and invest a lot of effort into making it realistic. So therefore, I don't know any example of new computer games, maybe something like GTA or so. The behavior of the traffic there looks quite realistic. And they also have interactions between cars and pedestrians and cyclists. They stop on the street and so on. So this is can be used quite well. And we also use their game engines, so for visualizations mostly, to visualize in our driving simulator. So our driving simulator is actually using a game engine from a video game to visualize the surrounding there. Not the algorithms, but the visualization is from games. Yeah.
Sorry. Okay. So AVs are not yet readily available or present around roads. I'm not sure in Germany if it's already like 50% or something. You mentioned that when you get data, well, not all car companies readily give it to you, and you just use drones to follow already existing ones. How does that represent the overall behavior of the AVs? Like, how can it react to non-AVs, and how can non-AVs react to that vehicle in simulation? Or how did you model it?
So the second part, I did not quite understand what you mean, but for the first part I can already answer, and then we can talk about the second part. So the first part is we for example, use drone data, and we not just look at one vehicle, but we look at all the vehicles in the surrounding. And then you see, okay, well, the vehicle distance to the next vehicle is reduced by 5 meters, 4 meters, 3 meters, and then we say, okay, what does the vehicle do? It decelerates. It, I don't know, the braking light switches on. So we can really see exactly what happens and use that data to replicate the behavior in a model again. So we copy-paste their behavior from reality and take it into our simulation, and you can really observe almost everything which is relevant for traffic simulation, because for traffic simulation, what is relevant? Accelerating, decelerating behavior, lane-changing behavior, and maybe turning behavior. That's all we need. Yeah.
So in response to the second part, were data captured from aggressive drivers?
So
and
since,
how would the AVs react to that?
Okay. Well, coincidentally, yes.
Oh,
I mean, we didn't actively have other, especially human drivers in front of the AV. So an aggressive driver or a very scared driver. But of course, in our data set, there's lots of different kinds of behavior types surrounding the automated vehicle. But we mostly were looking also at the behavior of other vehicles towards the automated vehicle. So not the vehicle which is driving in front and look how the automated vehicle looks, but we, for example, evaluate in lots of research projects how do human drivers react to an automated vehicle when they know it's an automated vehicle.
Actually, yeah,
that's important.
The
So,
AV, is it like with stickers saying
yes.
it is an AV?
So,
Also,
so for
people-
example, in one of the research projects, we had an automated vehicle, and it was a BMW, and it was looking like a regular car. So what we actually did, we installed lots of fake sensors on the roof and had lots of stickers, automated vehicle, and I think the cameras were larger than normal, so we had lots of fake sensors everywhere, so that the people really realize it's an automated vehicle. And then we tried to evaluate if the behavior actually changes. Actually, for car drivers, we didn't see any difference. And for pedestrians, we also looked into this field, and there was a lot of change, but I think it was very unrealistic change, because it was like, oh, automated vehicle. So they'd rather stop than doing, yeah. Yeah. So, yeah. I think you were first. Do we have time for that question? It's fine.
Just 5 minutes.
Okay,
Yeah.
okay.
But actually, if you have more questions, don't worry about that, because
Yes.
we have a second session. So.
And don't worry, I will join for lunch break also. I don't know if we all have lunch break together. I will also be here afterwards in the afternoon, so we can talk a lot.
Yeah, I want to ask whether, Professor, you have used the hyper-realistic digital twin system to do the simulator experiments, but here is the IQ confused it does. Sometimes we do the simulated experiment to control some factors, but if we use the digital twin system, just the scenarios is very different, and it's realistic. Sometimes we cannot control the geometry of the intersection interface like this. So how to treat up that?
Yeah, perfect. That's a very good question. We typically do that, therefore, 2 different kinds of digital twins. So one is a digital twin really representing the reality. And there, of course, you cannot control and say, well, I want this house to be more like on the left, and I want here a tree to stand here. That's not possible. Then we use artificial digital twins. So we create our own virtual city, which is not existing in reality, and use that for testing. So that's the 2 different paths we go. So, and for I think your first part of the question was also how realistic are they? It depends. I mean, we do sometimes have cities where we work together with, or we have research projects where we have really very highly sophisticated detection technologies. We have vehicles which have high resolution cameras and LiDARs to detect every single part of a building, and we even see if the curtains are closed or opened, then we can use that data for our highly sophisticated digital twin. Sometimes we only have information from the construction authority of the city saying, well, this building is 10 meters times 10 meters and 12 meters high, and we don't even know if there's windows or not because they don't have this information, and we just have a block being there in a twin, and maybe we put a photo of from the street side, from like Google Street View. We just attach it to this block of the building, but we don't have any information about, for example, if there's a glass material or whatever material. We don't have information if there's a window board is a little bit outside of the street or not. So it depends a lot on the data availability you have, and it depends a lot also on which experiments do you want to do. I mean, if we want to do driving simulator studies, sometimes it's not so important that the environment is super realistic. Sometimes the people, nevertheless, they should focus on the traffic, and the other thing is just visualization. Like, you don't really need that for your driving. But sometimes it's very important, of course, for sensor simulation of automated vehicles to have lots of details of the buildings. So it depends, yeah, case by case. This is the answer.
Okay, one last
Okay,
question for this
here.
session.
I may be in the different domain or department, so I have the different question about the environment and
Sure,
the safety. So people like feel perceive the safety is like a different mismatch between the actual safety and perceived safety.
Yeah.
So do you have consider this situation in your validation is like the bicycle truck in the middle instead of on the two sides of the alongside the pedestrian or something. So is there a situation that people will perceive more safer than actual complex or safety will achieve a higher frequency, like the people did use bicycle or vehicles in that situation?
Yeah.
Have you considered?
Yes, I mean, it's very important to distinguish between these two kinds of safeties. So we do that because we evaluate, of course, first the objective safety in terms of measuring the distances, measuring time to collision, measuring the post-encroachment time, so all these safety relevant parameters to really verify if a situation is really safe or not. But also, for example, in our driving simulator study, our test persons, they get health trackers. So we have some wristbands where we measure the blood pressure, what else? The sweat, I think, sweat level, yeah, heart rate. We also have a camera which is tracking their eyes. So if the eyes are like very fast looking left or right, and there's lots of like health or medical symptoms, let's say so, which we measure to evaluate if the person feels stressed or if it feels maybe scared. It's different. It's very difficult to differentiate between that. And we are actually not experts for that. So typically we have also support from the medical departments, which are helping us to evaluate this data and interpreting the data. If this is now a situation because they are cycling very fast on our simulator, or because they're stressed, or because they're scared, or because they're panicking. So yeah, at the end, we always get from them the information, this is stress level 80%. So that's what is done in such simulator studies. Yeah.
Okay, well, Martin is coming back in 10 minutes, so save your questions for the second session. Okay.
All right, thank you.